Good day, everyone. On behalf of Cambridge Health Tech Institute's Global Web Symposia Series and our sponsor, Ovizio Imaging Systems, I'd like to welcome you to Automated Inline Cell Culture Monitoring of CAR T cells in a closed-loop system. My name is Elizabeth Lamb, and I'll be the host and the moderator for today's event. Now, I'd like to introduce our presenter for today's event. He is Jan van Houwermeer, Vice President of Sales and Marketing for Ovizio Imaging Systems. Welcome, Jan. The presenter ball is yours.
Good afternoon, good morning for some of you. Thank you for joining this webinar today. We are going to talk a little bit about the challenges on CAR T manufacturing and how we at Ovizio can help you to conquer these challenges. So if we have a look at CAR T and its manufacturing process, if we start with the background, so last year during summer in August, the first CAR T cell construct was approved by the FDA. But still up to today, many challenges came up on the commercial scale manufacturing. And mainly that comes from, if we look at it from a historical standpoint, we see that at the start, the manufacturing process utilized at the clinical scale for the CAR T-based investigation on new drugs implemented very first generation manufacturing protocols and as well first generation equipment that really lacked the commercial applicability. So at the moment we need something on the manufacturing scale, new protocols that will be able to be scaled up as early as possible in product development lifecycle in order to be able to meet the anticipated commercial demand, of course. So the products must be scaled out to meet demand without sacrificing the product quality and the product process robustness. The key drivers in the process automation for CAR T manufacturing, some of you will know this very well. So they are, of course, critical to deliver a very safe, robust, and affordable treatment. So in order to do that, we would like to increase the automation. We would like to increase the closed loops and feedback loops in our process. We would like to increase the process feasibility and, of course, simplify a lot of the operations. On the other hand, we also would like to decrease the operator's variability, the hands-on time, and the cost of our goods sold, so the basic cost to manufacture our CAR T product. So the predictivity of the manufacturing outcome basically is based on the quality of the starting materials. So how would we at Ovizio like to challenge these opportunities in the manufacturing process? It all starts with images from our side. So we have three types of images: an intensity image, which you see on the upper left on your screen, a phase contrast image, and a 3D holographic image. And we combine that with refocusing capabilities. So that means that all cells floating around in a suspension culture will be processed in focus, no matter where they are in our flow cell. We combine all the information from those images with image analysis algorithms, and those algorithms are built with a machine learning platform. That machine learning platform allows us to generate very strong algorithms that will help you during the process. So it's basically a 5-step process, the way we analyze our images, which all start with the acquisition of the 3D hologram. So our 3D holographic image is the start of everything. It's followed by a computation phase where we already look at a few critical parameters on a cell. Then we detect the light cones, which are very critical for the viability algorithm. We do the refocusing of all the objects, and then we extract from the image on a single cell level what we call the holographic fingerprint of a cell. That holographic fingerprint of a cell is the start of or the basis where we base our algorithms on. So the holographic fingerprint of a cell is a combination of 70 parameters that are recorded on a single cell level. And it's a combination of morphological, optical, phase texture, and intensity texture parameters. So some of them are listed on the slide. All those parameters are then analyzed with our machine learning algorithms. So machine learning, for those who are, I would say, unfamiliar with the process, machine learning methodology is a methodology to create new algorithms without or with very little human interference. So if we want to create a new algorithm, we start with the creation of what we call a learning step. Very easily, that can be images of 100% viable cells and images of 100% dead cells. We present those images to the machine learning platform, and then the platform itself goes looking into the 70 parameters on a single cell level if it can identify any trends between any differences between the populations, any trends between the populations on any one, two, or all 70 of the recorded parameters. Once we know that, we go to step 2, which is the system training. Then we provide to the machine learning platform images where we know more or less there is a combination of 90% of cell status A or cell population A and 10% of cell status B or cell population B. And we make those mixtures in steps up to more or less 50-50. When that is done, the machine learning created or refined the algorithm that we are using. And then step 3 really is the use of the algorithm in standard processes. All this can already be done within a couple of runs. So some of the algorithms we have initially created within 2 or 3 culture runs, where we use images from the very beginning of the run to identify as population A, and where we use images of the end of the run to identify population B. This can be as easy as live cells and dead cells, or as complicated as viral infected cells versus non-infected cells. And then all the images in between are the known mixtures. And in the end of 2 runs, we can provide a new algorithm that's capable of identifying whatever is your need. So these technologies are implemented in 3 devices. The first one, the QMOD camera, and the second one, the engineering platform around the ILINE M, are mainly focused on adherent cell cultures, where the QMOD is even more for R&D and universities, and ILINE M more for manufacturing. And what we are going to talk about today is what we have done with the ILINE F microscope, which is specifically designed to work with cell cultures in suspension. So the ILINE F is the microscope itself, but comes with the BioConnect, and the BioConnect is what you could call an advanced sampling probe, and that sampling probe is able to collect samples, guide them towards the microscope where the images are taken, and then guide the sample back to the bioreactor to create a closed loop sterile environment which is able to which do not affect the cells at all or at any point. So the main features of the ILINE F microscope with the BioConnect is that it's inline. So the BioConnect is connected within the cell culture vessel. It's single use. The BioConnect is single use. It's label free. We do not use any reagents. We do not use any stains to have a look at the cells. It's a closed loop system. So there is no risk of contamination, and all the analyses are done in real time. At the moment, the key applications that comes with the software and with the ILINE F microscope are the total cell density, the viable cell density, viability, the viral infection kinetics, and phenotyping of different cells and cell populations within your culture. So our OsOne software, the main idea is seeing is believing. It allows you to have a look at your cells while they are in your culture, while they are running, while they are being processed, and at the same time to analyze the images that are being created by the ILINE F during the process. So it allows you to get access to the total cell density, viability, and viable cell density at any time. We provide you with a new data point every 30 minutes, which has everything inside. So it's already analyzed images every 30 with an end results every 30 minutes. You can follow your cell growth curve live on the screen. So that's being generated while you are watching. You can follow in real time the status of your cells at the single cell level. So you can access all the parameters on a single cell via the software. You can, of course, create feedback loops. The software is OPC ready, so that means that you can connect it to controllers or SCADA software and check and fine-tune the conditions of your cell culture. And the software is, as of now, as well, CFR 21 Part 11 compliant. So basically, that means that the machine learning platform connected with the OsOne software offers you an in-depth analysis of all the quality attributes of your samples. So the big question for today is, I would say, can we get both the CAR T cell production process and the ILINE F connected, and can we get an inline continuous monitoring of CAR T cells over their expansion? The short answer is yes. The longer answer, I will go into more details now with a couple of examples of what we have already done and what we are doing at the moment. So the first step is the integration of the ILINE F with a wave-back reactor. So can we basically modify or adapt our BioConnect to have an inline real-time closed-loop label-free phenotyping device in combination with a wave-back or rocking motion back cell culture vessel? And can we thus broaden the understanding of what matters biologically? So this is what we have done. We have adapted the BioConnect to fit the wave bioreactor. And on pictures, on the images, you can see the very first prototype. It has been by now engineered a little bit further. But the main answer, or the main question was, does it work? The answer is yes, it works. So we can, as of now, connect to, I'm not going to say all cell culture vessels, but at least to most of them, and at least to the very relevant ones. The second question, of course, will be answered via a couple of results and case studies. So how do we compare to reference methods, to current standard operation procedures, and what can we do with all the parameters that we gathered? So the first example is some results of CAR T cell expansion. So the setup is quite basic. So it was the use of the Xuri cells expansion system with a 2-liter expansion bag and a 1-liter working volume with a pH and a DO control probe. The CAR T cells were inoculated at around 1 million viable cells per ml, and the cells were grown for 3 days. The goal of this experiment was to prove that the OsOne software is able to continuously monitor all the T cells in the bag, and of course to count and discriminate the viability of T cells with strong correlation with an offline reference method. If we look at how we have done that, or what the analysis point was, so the continuous monitoring with the ILINE F microscope controlled by the software. Daily sampling was also done for the offline measurement on an automated Trypon Blue cell counting device from Beckman Coulter. So we were measuring or comparing viability, total cell density, viable cell density, and the diameter of the cells. And then, of course, there was a daily sampling for the offline pH measurement and adjustment. So this is how the software looks like in OsOne with the control panel. So what you see on the left side is all the data points at different points in time. They're are different images, of course. In the middle, you see the images generated by the ILINE F microscope. The images in this case are color-coded, where green means viable cells, red means dead cells, and yellow means small cell aggregates. If it's clear to you, so whenever there is an aggregate, you can see a very big yellow dot, which indicates an aggregate, and tiny yellow dots, which indicate the amount of cells within the aggregate. And that will be shown in the total analysis as well. And then on the right side, you see actually the measurements, as you would expect. So a viability, viable cell density, and then the graphs which are automatically generated on viability and viable and total cell density. So this can be followed and monitored over the whole run, over the whole process. Whatever, if your process takes only 1 day or it takes 2 weeks, that doesn't matter. So the software will run continuously, and the software will gather data continuously and process data continuously. If we look at the results and if we compare ourselves with the reference offline method, so the first way to do that is just make an overlay of the two graphs generated on one side by OS1 and on the other side by the reference method. So the small blue line is the results generated by OS1. The red dots are generated by the reference method. The first thing that you will notice is, of course, that OS1, because it monitors continuously for the whole run, you will get really a line with a point or a data point every 30 minutes or a continuous monitoring result, while with the reference method, with 1 or maybe 2 samples a day, you will only get 1 or 2 results a day maximum. The graphs align more or less perfectly, so that will already indicate that the results generated by both methods are very comparable. If we dig a little bit more deeper into the statistics of this, and we compare ourselves according and create or calculate an R-square score, then we see for TCD and VCD that the R-square score is very close to 1. So in both cases, 0.95. For viability, it's a little bit less, mainly because all viability scores or measurements are somewhere between 90 and 100%. So that means that there will already be a big offset when one method measures, for example, 93, while the other measures 94% viable cells. But the strong conclusion of the experiment that we did together with the customer was that the viability, the total cell density, and the viable cell density show a very strong correlation with each other. If we have a look at the robustness of the OS1 compared to offline reference method, then we use a bilinear regression. And in this case, so we add the 95% confidence interval, which are the blue lines. The average is the red line in the middle. And then you see that basically all points, or I would say 90% of the points, 90% of the results generated by both methods fall within each other's 95% confidence interval. So that means that both methods are really comparable to each other, and that results generated by OS1 are very comparable to what you're used to and what you're used to use in your day-to-day processes. What is also important to know is, can OS1 reflect the donor-to-donor variation? Again, the answer is yes. So, of course, not all processes will run similar. Some will start with lower cell density at inoculation. Some will grow much faster than others. Some will be a little bit slower. The viability might vary. And what you see on this slide is the results of 3 different experiments with 3 different donors. And there you can clearly see that not all processes are alike, but for every time, the results generated by OS1 or by the reference method are very comparable to each other, and our square scores are very close to 1. What was the next challenge? Of course, we are using 70 parameters. So the question we had was, with those 70 parameters on a single cell level, can we see more than just the viability and the cell count? Is there more information behind those 70 parameters that might be interesting for the field? So we can, with those 70 parameters, we can allow our algorithms to look at these cell classification systems, so create subsets, create differentiation states. Some of those are still under evaluation, but the first results are very promising. So to illustrate this feature, we will show you two examples. The first one is the discrimination of several blood cell types, and the second one is the monitoring of viral infection kinetics. So discrimination of blood cell types. The background was a question from a customer who is culturing white blood cultures which do not only have one specific cell type inside the culture. So they want to know, is there a way to accurate discriminate between the cells and count the different populations I have in my culture? So the challenge, or the big challenge, was, can we identify and discriminate different blood cell populations in a culture? There was a leftover of red blood cells in the culture, and then of course there is the granulocytes which with its subpopulations, and there are the lymphocytes. So the first step was creating images and identifying on those images the different cell types and creating, of course, the holographic fingerprint based on the 70 parameters. So you can see in this slide the different images that were used to identify and to create the fingerprint for the monocytes, for the mature dendritic cells, for the lymphocytes, granulocytes, and red blood cells. And then there was the algorithm that was based at first on a limited set of data, so only 100 cells per type in purified populations. And there already we saw very good correlations between what we predicted would be in the population and the actual population. So some of the relevant attributes that were used to discriminate cell types, I can show in this case 2 for morphology and 2 for the face, because it's a little bit confidential. If you ask it, we can explain a little bit or go into a little bit more detail on what other parameters are being used to discriminate the cell types. But if you see, for example, for the equivalent cell diameter, there is already a clear distinction between the lymphocytes, basophils, and the 3 other cell types. Circularity is a little bit more unclear, but still shows a difference between the lymphocytes, the monocytes, and the other 3 cell types. If we go into the phase parameters like optical height, mean, and optical volume, there again, there is the possibility to already extract information and to distinguish different cell types within one population. So this we can already do based only on 4 parameters. With 70 parameters, the discrimination becomes even more clear. So if we compare ourselves with a flow cytometer, which is often used in this case, then we see that we provide very similar results on the lower cell densities. So this was using only 100 images per cell. There was still some work to do on the higher cell densities, where we had access to a lot more cells per cell type. You see that the results are very much alike between Ovizio or the OsOne ILINE F combination compared to the flow cytometer. So as a conclusion, or as potential benefits, it is definitely possible with the ILINE F and with OsOne to check the homogeneity within a culture, or to monitor differentiation, wanted or unwanted, within your cultures. The second example, the monitoring of the infection kinetics. So the question here came from a customer and a university. is it possible within SF9 cells to see a difference between an infected or a non-infected cell if we introduce the baculovirus expression vector system? So can you count the different populations, and can you show a percentage of the infected cells in the culture? So here again, we would like to use real-time label-free discrimination, the data matching with an offline method based on a specific fingerprint for the infected or non-infected cells. So here you can see the images generated. If we would only use intensity images or phase images, the difference between pre-infection and post-infection would be very hard to distinguish. However, because we are using 3D holographic microscope, we have access to 3D holographic images, and there the differences became much more clear. And then it was really easy to extract the holographic fingerprints from infected and non-infected cells and to compare them with each other and to generate an algorithm that is capable of making a difference between an infected and a non-infected cell. On the OsOne software, not much has changed, just the addition of a few parameters and a few graphs. So now you not only have the total cell density, viable cell density, viability, but also the percentage of transfected cells. And of course, a graph generated automatically that shows the whole run and the status of the infection. So here the conclusion and the potential benefits are, of course, that the ILINE-F can be used while constructing the viral vector. So even before the whole CAR-T process starts and you are in the process of making your construct, the ILINE-F can be used to follow infection transduction processes. And the ILINE-F can as well be used to differentiate between engineered and non-engineered cells. We have very high hopes that this doesn't mean only by the use of infection, but maybe as well by using CRISPR-Cas technologies or any other technologies that you can use to engineer your cells. Now, I will go to the last slides showing what is next. So what is in the pipeline for the short future, where we would like to keep the balance between the proliferation and differentiation of CAR-T cells. So label-free identification of the lymphocyte cell types using our holographic microscope and machine learning algorithms. So getting multiple holograms of lymphocytes, establishing statistical classifier, and of course do quite quantitative analysis of all morphological and biochemical features that should be able to discriminate B cells, CD4 plus, and CD8 plus T cells. So among the list of 70 parameters tracked by the OsOne, some of them may help to discriminate different subsets of the lymphocytes, like the surface area, for example, or the cell volume, sphericity, the protein density, and the dry mass. As well on our product development pipeline is the gene therapy in a box and the ILINE-F. Can we integrate with black box or closed box systems that are on the market? We think it is possible, but some more development is needed. But of course, to make progress, everybody must take the first step, or at least somebody must take the first step. And like Mark Twain already said, the secret of getting ahead is getting started. So everybody interested in our technology is very welcome to work together with us on our next steps. Here are some references, people and institutions using our technology as of today. If there are any questions, feel free to ask them now or to contact me directly via email or meet us at booth 21 during the CAR-T Summit in 2 weeks. Thank you very much.
Thank you very much, Jan. I had one regarding the first case study that you did. You mentioned that you had grown the cells for 3 days. Have you taken it beyond that and tracked the growth?
Yes. So in the first case study presented, that was the standard process done by the customer. So grow the cells for 3 days. But we have experience in the antibody production, for example, where they easily do a production of 2 to 3 weeks, and it's no issue for the software or the computer to handle that much data.
All right, a question from one of our attendees. What instruments are you already working to connect with?
So in that case, I would say we can connect to basically any type of cell culture vessel. It's a little bit unclear to me what is exactly meant by what devices we are connecting with. So can person maybe specify this a little bit more?
Okay, Aletta, if you're still on, could you clarify which devices you are asking about so that Jan can better answer your question? Our next question, how do you achieve consistent sampling from the bioreactor?
So the BioConnect is in contact with, of course, with the bioreactor and with the medium. And there is a continuous flow of medium and cells through the sampling probe. So by standard, the flow of cells and medium in our BioConnect doesn't stop, which means that we very frequently refresh all the cells that are being imaged and all the cells that are in the BioConnect. So in the BioConnect, the cells don't stay very long in there to avoid all kinds of issues. And the flow is continuous.
All right, we've got several more questions that have just come in. Dharmesh says, I may have missed it, but how do you identify CD4 versus CD8 T cells?
Yeah, so that is still under investigation. I cannot and let's say go very much into detail in that, but let's say there is a very typical holographic fingerprint and a holographic difference between the two cells.
Excellent. Our next question is from Nick. The sampling and returning device, is this single use or does it require autoclaving?
Both. So it is single use, but as of today, we do not provide them sterile. That will be possible end of this year, beginning of next year. We will provide sterile BioConnects, but at this stage, they require one autoclave cycle, and then they can use the customer can use it once, and then throw it after one run, throw it away and use a new one. But
okay.
By the end of this year, beginning next year, we will provide sterile ones, sterile single-use ones as well.
Okay. Our next question, what do you think is the cause of the noise in the viability measurements in the early stages of culture?
That's mainly because the very limited amount of cells at that time point, because the cell density is still quite low. One or two more dead or viable cells in the field of view in the image might already have an influence on the total result, I would say. And once the total cell density goes up a little bit, the noise gets cancelled out as well. So that's, I would say, it's basic statistics. If you only have a low amount of objects or of cells, the impact of one object on the total population is quite big.
All right, and this is a comment followed by a couple questions. Matthew says, thanks for the great webinar. I'd like to know more about holographic microscopy. Are there any limitations as far as what illumination you can use?
We are using a very specific setup in our holographic microscope. It uses red LED light. The limitations on that not so much, but the setup that we are using is patented, and it allows us to make our instruments relatively small compared to other holographic microscopes. What is another advantage of the way we are using it is that we do not need to calibrate our device when using different vessels or when using different plastics, for example. I would suggest to the person, if they want to go into much more detail, to contact me directly.
All right. This same person had 2 follow-up questions to that. They want to know if the holographic microscopy is phototoxic, and what are the advantages or disadvantages of holographic microscopy?
Yeah, so it's not phototoxic. So red LED light is very low power light, I would say. The big advantages is that we can access all those parameters without the use of stains or reagents. So we can just image the cells and do analysis on the cells without the need to add anything.
Excellent advantage. Our next question, you showed another instrument in one of your last slides talking about the closed loop manufacturing. Could you identify that instrument?
Yes. I believe there are many brands, I think, but this particular one was the Milteni Prodigy, and we are working together with them to see if it's possible to connect the ILINE F to that device.
Ah, okay. Alex asks, have you looked into determining the naive characteristics of lymphocytes using this instrument?
No, not at the moment.
Okay. Nick asks, will any BioConnect devices be available already installed in any bioreactors, for example, pre-installed in the wave bag, or are you planning that the end users will be the ones who install these?
We would love that GE does that for us, but at the moment they are basically the limiting factor in that.
Thank you. And we have one more question here, although another one has just come in. Is it possible to follow the cell growth of different cell subtypes at the same time?
Theoretically, yes. However, the software at this point is not adapted to that. But theoretically, with the algorithms that we have, it's no issue.
Ah, perfect. Our next question, what are your thoughts on the accuracy of your viability measurement methods relative to the nuclear exclusion method?
I would say at the moment, no thoughts. I will need to investigate that a little bit further. So please forward that question to by email, and then I can discuss it as well with the product managers and software engineers internally.
All right, and I'll also make sure to forward that question to you as well. Our next question, are there any situations where you see deviations between the 2 methods?
Yes, let's say the biggest deviation comes from the use of 2 different methods. And sometimes we need to adapt the algorithm a little bit for very specific setups in between a reference method and our method. And the trend line will always be the same or very comparable at least. But the true values or the right values might sometimes deviate from each other. And that really is because of the use of different methods. Where we do see deviations all the time is in comparison with capacitance probes, which have it very difficult to distinguish between cell multiplication and cell growth. So when a cell becomes bigger, the biomass will go up as well, which doesn't always mean that the total cell density will go up. Whereas with our method, you will always see a difference when a cell grows or when the total cell density goes up. And there will always be a deviation in those cases.
Matthew asks, are there any plans to include sample retrieval for offline analysis? For example, it would be very useful to be able to characterize specific cells after they have been imaged for several hours or days.
So all the information on the cells is already available. So all the information is kept and all the information can be exported. You can even in the software click on one cell in an image and it will give you all the 70 results on the parameters. You can export it in a huge Excel file which contains all the parameters on every single cell that passed through the imaging camera. So that is possible. We are as well working, but then I'm probably talking 2022 on a device that's capable of handling offline samples as well.
Excellent. And our final question, do you require a single unit per bioreactor? For developmental work, we would normally run multiple bioreactors at the same time.
Yes. So it's at this time it's one-on-one. We have investigated to multiplex it, but because we are using optics inside the microscope, the cost to be able to build a device which with moving parts inside, which is so stable that the optics are not affected, are so high that it doesn't make sense to have one device that can multiplex, and it would cost much more than buying a single device for every bioreactor that you have.
Excellent. And we did have another question come in. Is it possible to multiplex sampling? For example, use one Ovizio system with various BioConnect devices running various cultures in parallel, and then have the software divide up the analysis?
No. So it's similar for as an idea. We are doing some new investigations, but let's say all tests so far showed us that at this stage it's really much better to have it one-on-one. It's better and cheaper to have it one-on-one.
Okay, perfect. Well, that takes care of all of our questions. I will also forward the questions along to Jan so that he can answer you in more detail directly via email. So with that, I would like to very much thank our presenter for today, Jan van Houwermeer, Vice President of Sales and Marketing for Ovizio. I'd like to thank Ovizio Imaging Systems for sponsoring today's event. And most of all, I'd like to thank those of you who came and spent this time with us. We hope you were able to get some information that will make life in the lab a little bit easier. So on behalf of Cambridge Health Tech Institute's Global Web Symposia Series, thank you so much and have a great day.